Indian Association of Structural Engineers, also known as IS-Struct-E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS-Struct-E is registered under the Societies Registration Act 21 of 1860. IS-Struct-E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IS-Struct-E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik, Shri Manoj Mittal and Professor R. Pradeep Kumar. As its president, IS-Struct-E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IS-Struct-E has collaboration with various international professional like-minded associations and institutions. IS-Struct-E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IS-Struct-E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IS-Struct-E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs, seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements, and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IS-Struct-E's activities are widely appreciated and known for quality technical contents. IS-Struct-E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines, and a monthly newsletter. IS-Struct-E's publications are becoming popular with time. IS-Struct-E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IS-Struct-E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IS-Struct-E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi to inculcate the professional culture and provide handholding to the budding engineers. IS-Struct-E has its student chapters in several leading engineering institutions as well. Membership of IS-Struct-E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IS-Struct-E is available on its website www.isstruct-e.co.in.
Yes, sir, please start.
Vikas, shall I
Yes, sir. Yes,
start?
yes, sir.
Dear friends, welcome to this webinar topic of today is on insights into cable aerodynamics. The speaker is Dr. Lakshmi Parmeshwaran. She holds a PhD in civil engineering from IIT Roorkee and has more than 37 years of professional experience, which includes research, teaching, and consultancy. She was a chief scientist in bridge engineering and structural divisions of CSIR, CRRI, New Delhi, and a professor of engineering of science. Her area of research includes wind engineering, bridge engineering, and sustainable construction material. She had successfully completed aerodynamic studies on cable stayed bridges, Yamuna Bridge at Allahabad and Burdwan Bridge, wind tunnel studies on chimneys, cooling towers of various thermal power stations, and wind-resistant design of microwave towers and TV towers. So regarding the brief of the topic, this is a cable aerodynamics, which refers to the study of interaction between approaching wind and cables, particularly in the context of cable supported bridges and roofs and transmission lines. This presentation will be focusing on aerodynamics of stay cable systems used in extra doors and cable stayed bridges, especially aspects related to wind and cable shape, orientation, and damping. Aerodynamic forces acting on cables and in the measurement using wind tunnels, cable vibrations and oscillations, and various mitigation measures for wind resistant design, illustrated with some examples. Understanding cable aerodynamics is crucial for achieving wind resistant design of stay cable systems and ensuring structural integrity by mitigating oxidation and minimizing the risk of damage. Now I request Madam to just share his experience and knowledge. Madam, now you proceed.
Thank you, Dhawan sir. I'm just sharing my screen. Are you able to
Yes,
see
ma'am.
my screen?
Yes, ma'am. Yes, ma'am.
And also you are able to hear me?
Yes, ma'am. Clear, loud, ma'am.
Good evening. I thank Dr. S.K. Devan for giving me this opportunity to present the insights into cable aerodynamics. And the reason why I have selected these topics is like large number of cable suspended bridges, like cable stayed bridges and extradose bridges are being built in our country. And the cables, they are the main tension elements, and these elements are supplied by by the structural designers. So what minimum they should check about these cables to make sure that the structure performs well after incorporating these cables. So this is my intention, I will try to speak on this particular topic. So here, I'll be explaining cable as structural elements, like where they have been used or where they can be used. Then we should know about the cable, its dynamic characteristics, uh, about the frequency, what are the parameters on which they are dependent on, and about the damping. Then comes the interaction of cable with the wind, because of which there will be the drag and lift forces, and also there could be some aerodynamic damping also. Then there are vibratory phenomena like galloping, vortex-induced oscillation, rain-wind-induced oscillation, buffeting, and also cables, like in cable-stayed bridges, they are supported on the deck. So if the deck get vibrated, that get transmitted to the cables. So there could be some vibration there. And I would like to give some tips for cable vibration mitigation, which are being practiced. And there can be some surface modification of the cables, or there could be some installation of different type of dampers, or it could be some structural design measure to eliminate the internal excitation. So I'll be throwing some lights on these aspects. So when we see the use of cables in structures, like the first thing which came into my mind is the transmission line tower, which is a wind sensitive structure. And you can see that the various arms, they are carrying the conductors, and the conductors are having circular cross section. And they have been subjected to oscillation because of wind. Like there could be some low amplitude oscillation because of vortex induced oscillation, or mainly the transmission line conductors, the cross section of the conductor gets changed because of the accumulation of snow or ice during the winter months, because of which they are subjected to some divergent oscillation, which we call galloping. And you can see here, they are using the dampers, they are using the spacers. These are for minimizing the oscillatory effect of these conductors. And this is in practice way back in 1900, early 1900. Another example is like a guide mast where there is a light frame which is being held or stabilized with the use of wires or guide cables. And again, it is subjected to the wind forces, wind sensitive structure. And the third one in this category is the cable suspended roof, which gained a lot of attention during early 1950s. And cable suspended roofs, where the cables are used to carry the roof load, and they are provided mainly to span a wide area like stadia or some sports arena or other fields. Like I can give an example. This is the 1972 Munich Olympics stadia, and another one is the University of Chicago. They have again a sports arena where you can see the cables suspended roof has been provided. And in this regard, I would like to tell that our guru, like Professor Prem Krishna and Professor P.N. Godbole, they have a book on cable suspended roofs. In fact, the first edition of this book came in 1970s and the second edition in 2013. So probably the structural designers, they can use this book if they are interested in doing a design of such roofs, because now the cable supported structures are gaining a lot of importance. I'm sure that probably the next thing which will be coming in line will be cable suspended roofs. Now, the application of cables in bridges, you can see like they are used in like suspension bridges where the suspension cables are there, which forms a catenary, and also there are hangers provided to carry this deck. And you can see the suspension bridges of very long spans, and also like they are being used for pedestrian users like in our hilly terrain like Uttarakhand, etc. So the cables again become an important element here. And another form of cable use of cable is definitely the cable stayed bridge. Again, like you can see, the cables can be in either in one plane or two plane or three plane, and also the inclination of the cable that also varies. The spacing of the cables vary in the cable stayed bridge. And third category of this is like you can see the arch bridges, which are also gaining a lot of importance in our country, and especially the network arch where the cables are there. So that is also coming up in a big way. And another important type of structures which are coming or being built, that is the extrudos bridge, where again like the cables are being used. So we have in the Indian Road Congress, there is a special bridge committee, and it has recently come out with this IRCSP 136, which is for the cable stayed bridge, IRCSP 137, which is for the extrudos bridge, and IRCSP 145 for the arch bridges. It covers not only the network arch, but like masonry, concrete, and steel arch bridges are being covered in that. So this is just an how like they can be used in various structures. Now, like we focus on the stay cables which are used in cable stayed and extrudos bridges. Basically, like we have this parallel strand system, and you can see that they are being used where like each strand is made of, like you can see that 7-ply wires, and each wire is of diameter of 5 mm. Only thing, the central one has a diameter which is more than 5 mm, and the tensile strength of these strands, that is 1860 MPa for 15.2 mm and either 1770 MPa or 1860 MPa for 15.7 mm diameter. And then like when we think about the stay cables, it is not only like their strength, but also we need to pay attention to their corrosion protection. So that is also important. So it has been provided with this HDPE, that is high density polyethylene pipe. HDPE pipes are provided, and also each of these strands, you can see that they are galvanized also. So this is one popular form of stays which are being used. Another one is the new parallel wire system. Again, the cables are of 7 mm diameter with tensile strength of 1570 MPa to 1770 MPa. So that is also another type. And earlier, like you can see that in some of the existing cable stayed bridges, you see this log coil system. And here again, like you can see that the outer layer, you can see some special Z type wires are there, and there is a inner core where, like, you can see the rounded wires are there, and they generally have a tensile strength of 1370 to 1570. And another type is the epoxy coated strands. Again, the 7-wire assemblies are available. Again, like you can see that now the PE sheathing for this epoxy coated uh, field strands are also available, and they are preferred because of the uh, susceptibility of this epoxy resin to the use of prolonged UV light radiations. So what we have seen is that there is an increase in the strength of the cable which are being used, and also the corrosion protection that is also being gaining lot of importance because of the design life of 100 years to be achieved. So if we see that the cables in the suspension in the cable stayed bridge or extradose bridge, like different cable arrangements are there, and this is a harp arrangement in this bridge. This Veer Kanwar Singh Setu or Ara Chapra Bridge. This was constructed in 2017, and total length is for 4,350 meter, and it is a multi-span extradose bridge, and 16 spans are there, and each span of 120 meter. And you can see the 5 cables are provided, and pylon height is only 18 meter, and there is only one plane of this cables provided, because generally this extradose bridge, they are provided with PSC box girder deck. And then the harp system, basically it's preferred because of the point of view of aesthetics also. But what I have seen is that in our IRC SP 136 and 137, there is an appendix given which gives details about the bridges which are there in India, and also like the various dimensions and the type of the deck and the tower, etc. But I found very little information we have been able to collect with respect to the cables, which are very, very important, especially related to the diameter of the cable, length of the cable, and type of the cable which have been used, or whether some dampers have been used or not. And this is the second Hooghly Bridge, which has a total length of 823 meter, and main span is 457.2 meter, and there are 2 side spans of 182.88, and it has a wide steel concrete composite deck of 35 meter, and 6-lane traffic is being carried by this particular bridge, and it has a clearance below the deck of 26 meter, and H-shaped steel pylon has been provided. And you can see here that there is a fan arrangement of cables has been provided, and you can see that most of the cables, like, they are very spaced very closely at the top of this particular pylon. And this is the bridge, the Rusky Bridge, and 4-lane bridge. Again, like, it is a 29.5 meter deck width, A-shaped pylon with a pile foundation provided, and clearance below the deck is 70 meter, because wherever there is a navigational requirement, so there the clearance below the deck is more. And pylon height is A-shaped pylon and 320 meter, and it has been provided with 168 cables and parallel wire strand that has been used. And you can see here that the shortest cable is 135.7 meter and longest cable is 579 meter. That means, like, this bridge, like, the longest cable, that is the length of the cable, is increasing along with the span of the bridge. And this is another bridge where, like, you can see that a single pole pylon is provided, and there are 224 cables provided, again parallel wire strand, and longest cable is 540 meter provided, which carries a deck width of 53.3 meter. That means nowadays what we are seeing is the number of lanes which are carried by the bridge is increasing, and the span is increasing, and also the number of cables that is increasing, the cable lengths are also being increasing. So you can see that if you see how the length of the cable has increased over a period of time, because I think though the cable stayed bridge gained momentum after the Second World War, like the Tatara bridge, like it was having a cable of length 462 meter. Then the Sutong bridge, which I saw, that is 577 meter. Rusky bridge 580, and the third Bosphorus bridge 597, and this Changtai Yangtze River bridge 633, and the one which is being under construction, that is 649. So this is the how the length of the cable of the bridges are being increased with the increase in the span. So this is one thing which we structural engineers we need to understand. And what happens when the length of the cable is going to get increased? Because some of the existing cable stayed bridge, most of them, like they are being instrumented, and the vibration characteristics and other aspects are being monitored. So what they have seen from the field measurements by the various researchers, example on Sutong Bridge, Husung Tong Yangtze Bridge, and another bridge in Korea, etc., they found that when the cable length is increasing, basically the cable fundamental frequency is going to get reduced, and the number of cable modes in the frequency range which are sensitive to rain wind induced oscillation, that is going to increase. Then wind speed corresponding to high mode cable vibration induced by vortex induced vibration, that is going to get decreased. So what a designer is to has to pay attention is to focus on achieving cable multimode vibration mitigation. That means number of cables are going to get excited when the length is going to increase. So now the question comes like, what is the minimum length which one has to start pay attention, and what are the vibratory oscillation mechanism one should look into, and then how we can mitigate these oscillations. So for this purpose, we need to understand the cable aerodynamics. Basically, as I explained earlier, aerodynamics is nothing but it is an interaction between the structure and the wind. And here it is cable and wind, so it is cable aerodynamics. And because of this interaction, it gives rise to this drag and lift forces, and also these aerodynamic oscillations like rain wind induced oscillation, vortex induced oscillations, galloping, buffeting, because of the turbulence which is present in the wind, approaching wind, depending upon the terrain on which the bridge is being constructed. And then support induced cable vibration. And as a structural engineer, we need to pay attention whenever the cable length is going to be more than 80 meter. So that means the first question point is we have to see what are the cable lengths, and if the length is exceeding 80 meter, then we need to consider that whether it is a extradose bridge or a cable stayed bridge, it doesn't matter. But if the cable length has increased more than 80 meter, we need to pay attention. And coming to the dynamics of the cable, basically, this is the equation to calculate the time period for nth mode of the cable. And you can see that it increases, the time period increases with the length of the cable, and it is and directly proportional to the square root of mass of the cable. And then another aspect is the tension in the cable. So you can see that in the cable stayed bridge, basically it is a cable which is held with under tension. So you can see that these are the parameters, that is you need the length, the mass and the tension in the cable to find out the time period, and frequency is nothing but it is inverse of the time period. So once we calculate the time period, that is if the time period is going to increase with the length of the cable, that means the frequency is going to be reduced. So, and we need to worry more about the cable with respect to the frequency. That is, if the frequency value is lower, we have to pay more attention with respect to the wind-induced oscillation. And I explained you that there are these low coil cable system and parallel strand system. And these are some of the existing bridges, not in our country, but other countries where like they have measured like what is the damping in these cables. And you can see that the damping ratio in all these, whether it is low coil or parallel strands, they are all very, very low. That is, the damping ratio is like 0.001 or 0.005, like that. So very low damping. That means the inherent damping of the stay cable is very, very low. So we need to understand that with the increase in the length of the cable, the frequency is going to come down, and the damping of these cables, they are also very low. So what we can do to minimize the vibratory amplitudes, that is the thing which one has to pay attention as structural engineers. So the inherent damping of stay cables, I think from the previous slide, like we understood what based on the measurement, but even the PTI guidelines or the Chinese guidelines or CETRA documents, etc., they are also specifying depending upon whether it is a cement grouted cables, which were earlier used, now not being used, but what is the damping value. And you can see they are all in the same range what the field measurements are telling. So there is a lot of, you can say, compatibility between the field data and what is given in this specification. In fact, these guidelines have been prepared based on the field measurements. And the similar recommendations have been given in IRC SP 136 also. So here we say that for preliminary estimation, we can take the critical damping ratio as 0.1% for all type of cables. And also, like, we can get the details from the cable manufacturer also, as I said earlier, because they are supplied and they are proprietary items also. So I think we need to get the damping corresponding to a particular type of cable from the manufacturer. And you can see that for various strands, how they vary, and also it can be calculated if you know the length of the cable, because as I said, it varies with the length as well. So that also can be calculated. So one thing we have to keep in mind that with the increase in the length of the cable, the frequency is going to get reduced and they have very low inherent damping. Now comes the wind forces in the cable. Actually, like we have seen number of cable stayed bridges in previous slides, and that means the wind is acting on the cable system. So cables in the wind force on the cable system itself with the span enhancement is about, say, 30 to 40% of the total wind force to which the bridge is subjected to. So though like they are small in diameter, like you cannot ignore them. You have to pay a lot of attention to it. And in this case, like the cable is circular in cross section, and there, like the force coefficient, basically it depends on how the wind is going to flow around it. And also it depends on the velocity, what is the kinematic viscosity, diameter of the cable, and what is the surface roughness of that particular cable. And we know that for circular section, basically the drag coefficient, that is a function of Reynolds number. So basically, because of the dependency on Reynolds number, the force coefficient also varies with the Reynolds number, because the weight around the circular cross section, that is going to change with the Reynolds number. So just to give you an idea how do you compute the stay cable, I know that all of you know about it. Basically, it is, I think there is a mistake. It is actually FD is half rho VZ square DC into CD into G, and rho is the air density, and VZ is the hourly mean wind speed, and G is the gust factor, and CD is the drag coefficient. As I told you, that the drag coefficient depends on the Reynolds number. So what we do is we generally take the diameter and find out what is the velocity at the site, and then like if the values multiply them together and it is less than 6 meters square per second, then we take a value of 1.2, and 0.8 if DC VZ is more than 6 meters square per second. This is what is given in IS 875 part 3 and IRC 136. Now the question is, we have given this 1.2 also and 0.8. But this 1.2, this may be useful, like if you have some hangers for the suspension bridges, there like the diameter may be very small and there this condition may be satisfied. So there we may use this 1.2. And this we may use like for cable stayed and extrudos bridges. So I think this I will correct. There is a mistake here. And how do you get the drag coefficients, etc.? Or like if some certain surface modification is done, how the efficacy is verified. So that is generally done using a model study in wind tunnel, or nowadays like this computational fluid dynamics softwares are available like Fluent, like where like one can do a modeling also. So these are some of the methods by which like we get the aerodynamic coefficients. This is a old literature of Normandy Bridge, because Normandy Bridge, when it was constructed, it was one of the longest at that time. So there, like they have studied again the cable in the wind tunnel to get the drag and the lift coefficient. And you can see here, that the values are maybe around 0.8 what they got, because if there is some roughness around the surface, that also will add to the drag coefficient of that particular element. And again, like this is some studies done by FHWA, and they have done the drag coefficient for various cables which are inclined at different angles. And you can see that they have got a value of around 0.7, like for up to 2.5, they have got. Actually, like as I said that, like when we do a wind tunnel testing for a circular cross section, basically a drag bucket is formed. And generally we don't take the values which fall in the drag bucket, but we generally either try to do it in this particular region of the Reynolds number. That is, either you do at a lower Reynolds number or at a higher Reynolds number. But higher Reynolds number will require a large wind tunnel. So probably we do it for a lower Reynolds number, but it has to be a stable value. That value only we can select for the design of the these components. So that's why we have to be careful about the simulation of the cross section of the model in the wind tunnel, and also like at which Reynolds number we are doing it, and it doesn't fall in the drag bucket region. And you can see that like it has very low, you can say the drag is on the higher side, 0.7 or 0.712, etc. But here you can say that they are on the lift values are on very small in that particular region. And another important aspect I would like to mm, focus on is about the aerodynamic damping. See, after we got the drag coefficient, and if we know like the diameter of the cable and the wind speed, the mass and the frequency of the uh, uh, vibration, then we can work out what is the aerodynamic damping in the direction of wind and also in the transverse direction of the wind. And you can see here that like in the transverse direction, basically the damping, aerodynamic damping get halved in the transverse direction in comparison to the direction of the wind. And why this aerodynamic damping is important is like we earlier discussed that like we have very low damping for the cable. So some aerodynamic damping, because the sometimes the damping which is from the wind, that also tries to stabilize the system. But there could be another aspect of it, that is the aerodynamic damping may be negative, and at that stage like we find some divergent oscillation like galloping, etc. So the aerodynamic damping, that is also important, especially like when I discussed about the conductor, transmission line conductor, where the cross section is going to get modified because of the accumulation of ice. There could be a possibility of galloping, and there that could be because of the negative aerodynamic damping. Now coming to the rain wind induced vibration, basically again like this was a concern and observed in many cables, I think in Japan from 1988 onwards, but even in the Sutong bridge in 2019 they say that they have observed this rain wind induced vibration. And based on the field measurements on various bridges and observations, now the general characteristics that has been well established, and lot of windtunnel studies where the rain was also simulated that has taken place. So they found that now the frequency range of the cable, that is 0.3 hertz to 3 hertz, and if the wind speed in that range is low, it is only just 5 to 20 meter per second. I think this is the normal wind speed which can be there on any day. And if the cable inclination is between 20 to 45 degree, then like these cables may be subjected to some rain wind induced oscillations. So that means like we have to consider, we first said that like up to more than 80 meter long cables. Now we say that if the frequency is between 0.3 to 3 hertz, up to that, like we may have to consider the cables with the inclinations of 20 to 45 degree, and not at a high wind speed, but it can happen at a very low wind speed of 5 to 20 meter per second. So we cannot ignore that. So how do we check the susceptibility of rain wind induced vibration? Because essentially the rain wind induced vibration occurs because there is only when light rain is there and also low wind speed is there is the rain drops are formed on the surface of the stay cable, and its position with change in position that can excite the cable. So to avoid the onset of vibration, basically we need to check the Scruton number calculation. Scruton number is nothing but the mass into damping ratio divided by rho dc square. So where the mass is cable mass per unit length, and delta is the logarithmic decrement of the cable. So we get the damping ratio as 2 pi delta. And so first we know that like we are assuming this 0.1% for the cable, but like we can use this particular equation to set how much damping is required so that like this particular cable will be stable with respect to the rain wind induced oscillation. So Scruton number is to be used to decide about the damping requirement for the cable. And suppressing this rain wind induced oscillation, required damping is about 0.5%. This is as per this PTI document and also FIB Bulletin 89. And again, like as I said, that the multi-modal oscillation of the cables needs to be considered. So how many cables to be considered? That is still a debatable issue. For short cables, like we can consider first 3 to 5 modes because that may be happening in 0.6 hertz to 3 hertz, or say you can say 0.3 hertz to 3 hertz. But you can see that though I said that 0.3 is the lower limit, but the Sutong bridge, they found that like even the long cable with 0.23 hertz, that was also susceptible. Actually, almost 14 modes have a frequency lower than 3 hertz in that particular case. But what is more difficult is that a damping ratio of 0.5, how it can be achieved for all the modes, that is a big question mark. So there are still some more research needed how this can be achieved. So this is a challenge if the length of the cable is going to exceed. So this is just a you can say a figure to show how the inclined cable under the wind that is being tested in wind tunnel. So wind tunnel studies and field measurement studies that has given about more details on rain wind induced vibration. So one aspect is to enhance the damping, okay, and another is to carry out some surface modification of the cable. And you can see that this is the helical fillets on HDP pipe, and there could be some indentation on the HDP pipe also, it can be there. Okay, again, like why we are providing this surface modification, basically we want to prevent the occurrence of water droplet on the surface. So that can be achieved by the surface modification. But at the same time, we need to ensure that the surface modification is not going to enhance the drag coefficient of the cable. So that also we have to keep in mind, because the drag is getting increased means the wind forces on the cable system is going to increase. So we should adopt a surface modification such that the drag is not going to increase. At the same time, the water rivulet is not being formulated on the surface. And when the cable pipes have effective surface texturing, then earlier we saw an equation where the Scruton number has to be more than 10. But if we are providing the surface modification, then there is some like concession with respect to the damping. That means like rather than using only dampers, like you can have a combination of surface modification along with the damper, so that like you can achieve this Scruton number more than 5 means if the surface modification is provided, then like you can probably eliminate or this phenomena of rain wind induced vibration. And another phenomena is the vortex induced oscillation. As I said, this happens in circular conductors also, because when the wind is approaching the circular cross section, like it separates, and then like the eddies are formed on the wake region, and these eddies, while it are being formulated, it excites the circular section in opposite direction. This is the approaching section, and it is across the section the vibrations are happening. Again, like when the shedding frequency coincides with the frequency of this cable or the conductor or circular cross section, then the resonance happens. And here, like we check the susceptibility of the vortex-induced oscillation. That is, again, this is a phenomena which happens at low wind speed. So to check the susceptibility, we use a number called Strohal number. So here, like this VCR, that is the critical wind speed for vortex-induced oscillation for each of the cable needs to be checked. And if it is on the lower side, that means like just like we said 5 to 20 meter, like that, in that range, if it is happening, then we need to worry about the oscillation of vortex-induced vortex-induced vibration. So again, like the Strohal number of the cable without any damper, that may be less than 1. But if the Strohal number, again, you work out the Strohal number, and if it is more than 2.5, then that indicates that the vortex-induced vibration is restricted. So one thing is the check the susceptibility using the Strohal number, and then use the Scruton number to find out whether it is susceptible to like vortex-induced oscillation, or like whether it is safe with respect to the you can say rain wind induced oscillation, and or how much damping is provided to make it safe with respect to VIV and RWIV. That can be estimated with the help of the Scruton number. And the third category is the galloping. Again, galloping can be a dry galloping, or as I said, the ice snow accumulation induced galloping. That is the cross section of the cable itself getting modified because of the ice accumulation, or it can be a wake galloping. So wake galloping means there are two cables which are close to and the one lies on the wake of the other. So the approaching wind characteristic get modified. So that is what we call as wake galloping. So when there exists a component of wind velocity not normal to the axis of dry inclined cable, the dry galloping may happen. Actually, the cable vibration of large amplitude oscillation, actually this ice snow accumulation, that is if we are having going to have a cable stayed bridge, maybe in Leh, Ladakh area, or like Srinagar, or some Himalayan region, like then like we have to worry about this ice snow accumulation on the cables. And also like nowadays, like the aesthetics of the cable stayed bridge, that is improved with the help of the lighting. So if we have some decoration lighting, that also may change the cross section. So select a lighting such that it is not going to modify the cross section of the bridge, cross section of the cable. Then how to prevent the ice snow accumulation? Actually, that can be suppressed by preventing by some supplementing damper, or careful aerodynamic examination is required before the installation of decoration lighting attachment on the cable. And this is the wake galloping which I was telling. Actually, like the spacing of the stays, they are very important. So that needs to be checked. So the cable which is there on the wake of the other cable, that get excited. So that sort of vibration can happen in the case of suspenders of the suspension bridges also. So the spacing of the cables, maybe like at the deck level, they are quite wide apart, but at the like the fan arrangement, maybe at the tower top, the spacing of the cables, again, there like you may have to check how much they are. So that is important. So wake galloping, that is when two cables are aligned parallel and close to each other. The downstream cable can be forced into unstable oscillation, which are called wake galloping. Actually, it depends on the spacing. So the spacing, again, that we express in terms of the cable diameter. So if they are very close, that is 2 to 5 times the cable diameter, then the wake galloping happens. So that means like the spacing between the cables that need to be more than 5 times the diameter of the cable. That is the simple check you can do when you decide the cable spacing, not only at the deck level, but also at the tower top, or where the anchorages are being done. There also you can see. Now, like comes to, we have seen the surface modification. We have seen about the dampers which can be used, like just to get an idea how much damping is required to be provided, so that like the cables are safe with respect to vortex induced oscillation and rain wind induced oscillation. And also we found that the frequency of the cable, that is a function of length. So one method to control the cable vibration is to interconnecting the cable with cable ties. And basically the cross ties are basically a temporary measure which will help to reduce the length of the cable, and again like the frequency values are going to change. And also like whenever like the deck frequency and the cable frequency are close, there also like we can use these cross ties to separate the frequency values of these two elements. And also installation of these cross cables that increases the damping. And you can see that these cross ties are used in number of bridges, like they are employed to change the frequencies of the cable in the vertical direction. And but one thing is there, like this can be used like as a temporary measure before the installation of the dampers, because these cross ties also needs inspection, maintenance. And also like when you have these cross ties, I think the inspection of the other main cables, that becomes sometimes difficult. And also, but this is one you can say cheap solution. So maybe like some provision can be provided for the stay cable system, so that like in case like you require, like you can provide these cross ties so that like you can stabilize the system without much problem. So that sort of arrangement can be done. Now coming to the different type of dampers, because the objective of the damper is to reduce the amplitude of cable vibration. And we said that some additional damping is required based on our Scruton number requirement. So 3 to 4% logarithmic decrement that may be required to suppress the vibration. And what type of dampers are available, like viscous dampers? You can see this is a dashboard provided for the mathematical formulation. Here stiffness and damping both are there. So viscoelastic damper, or like some friction dampers are there, where it is a function of the friction coefficient and the stiffness. Some high density rubber dampers and tune mass dampers. There are different type of dampers which can be used. Now the question comes like what are the type of dampers available and where to provide them? Basically, like you have the internal dampers and external dampers. There are two type of dampers available. And internal dampers that require a stiff support. So generally it is provided like at least like 1.5% of the cable length from the anchorage. So that means like if you have a 400-meter long cable, then the internal damper can be placed like at about 6 meters from the anchorage. And like the suppliers of these PSS and NPWS cables, they have actually different type of internal dampers. They have developed them. And also like the effectiveness of these dampers, like we have find out based on the field measurements. I will touch upon that aspect also. And only this log coil system like there, they don't have any internal damper developed. So this PSS or NPWS system, they are getting popular because these internal dampers can also be provided. And also one can have a provision for installation, future installation of external dampers if necessary, if it is the case of longer cable. So the internal damper, like you can see that there is a ring shape and it is installed inside the guide tube, which in turn is fixed to this formwork tube. And the internal dampers, they use to dissipate the energy by distortion of the dissipating material. In this case, it is a rubber. This is a strand and this is a rubber. And in case of internal damper, the dissipating material can be specially formulated rubber. And they are always installed, as we discussed, that it is near the anchorage at the lower end of the cable stay at 1.5 percentage length of the cable. And where like these cables, that is the internal elastomeric damper, where they are uses, they can be used like for a length of cable like up to, like you can say, 150 meter, they will be useful. Then more than that, like we may have to go for some viscous damper. Again, like we have to understand that the viscous damper that allows the deformation along the damper axis. So that means it provides damping only in one direction. But in generally, the cables may have like vibration in two axes. So at least like we may have to provide two dampers rather than one in that particular case. Or there are certain dampers available which can be used for cables more than 150 meter also. That is the internal hydraulic dampers, where like it can control the oscillation in all the three planes that can be done. So there is lot of development, that is advancement in the technology of the dampers. So we have seen that internal elastomeric damping that can be used like for cables lower than 150 meter and more than 150 meter, like it is preferable to go for this viscous damper. Then viscous shear dampers, they are also used and widely used in Japan and China. That is also another type of damper. And another type of damper is the friction damper, which has a sliding interface that would dissipate the maximum of mechanical energy while keeping the threshold amplitude below a certain specified acceptable limit. And one thing we have to understand that the friction dampers can provide frequency independent damping. So that is the advantage of this particular damper. So that is one advantage. One thing, but we have to understand that the friction dampers, that is characterized by a stick slip motion. So the behavior prevents the damper from being activated at small amplitudes. That is once it is activated, that means like the cable, the oscillation will get damped very rapidly, but very small like amplitude means it will be in the stick position. That means the friction interface is stick, means the damping effect will be very small. So these characteristics also we need to understand. And like these are the external dampers like one can have for again like fixed type and pendular type dampers are there for very long cables. So again based on the fixed external type, that is based on the hydraulic damping criteria. And so we have seen the different type of dampers. We have seen the aerodynamic modifications which can be done, that is cable surface with dimples or a helical wire. Now the question is, what is the minimum thickness of the helical wire required to suppress rain wind induced oscillation. So it has to be less than 2 mm. You can see that a very thin helical wire is required to suppress the rain wind induced oscillation, that is lower than 2 mm. But if you want to suppress the vortex induced oscillation, there you need a thick wire that is more than 10 mm. For wake galloping and vortex induced oscillation, you need a thick wire. A thin wire is required for rain wind induced oscillation. And as I said earlier, as the length of the cable get increased, like you can use a combination of that is aerodynamic modification, geometric modification, external dampers or internal dampers. All of them you can use, and they have been successfully used in many of the existing cable stayed bridges. And just to give you why we need to worry about these various oscillation of cables, you can see that even small spans like as small as even 130 or 186 etc., there an amplitude of 0.6 etc. meter was seen, and you can see that the maximum is about 2 meter. That means the high amplitude oscillation can also be there for the cables even when the span lengths are not that high. So we need to pay attention to the measures which can reduce the oscillation. So these are some of the cross ties, as I said, that will help to reduce the length of the cable, and also it will separate the frequency values from that of the deck. So now the case of a very, very long cable, you can see there can be an internal damper where the cable is getting attached to the deck. There can be an internal damper where it is getting attached at the pylon top. There could be some tune mass damper. There could be some external damper. There could be some, you can say some spacers, or you can say some cross ties, etc. So there could be a number of possibilities, like when we want to control the vibration of these stay cables. Now the questions come like how to measure the performance of these cables. That means like we have to measure what is the frequency of these cables and the damping in these cables. One is without the installation of the cable and after the installation of the dampers also. So here I would say that the accelerometers are generally fixed from the cable, so that like we can get the the characteristics. But the question comes how to excite the cable. So you can see that to excite the cable, you have to attach a string, not near the anchorage, but near the top, and then like it can be pulled and released so that the cable get oscillated. But the question comes like whether that is sufficient, that can give sufficient force when the length of the cable increases, and also the mass of the cable is also quite high. So there like you can use a motor and a release hitch, and then again like you can excite the particular cable. But this sort of arrangement may be useful for like small cable, and even I think so for some cables, like even the vibratory characteristics can be monitored at the ambient wind condition. But what happens is that at that time, like whatever you measure, the amplitude values are very low. So the damping, there could be some large variation in the damping value what you measure. But there are certain cable vibrators also that can be attached to vibrate the cable. And another method is that like you excite the deck, so that when the deck get excited, the cable also get excited. I think this we have also used in some of the bridges, not the cable stayed bridges, other bridges, to excite the deck. That is, you can keep some you can place some log or something on that, or some obstruction, and allow the vehicle to jump that obstruction, and because of that, the deck will get excited. But you can see that these are the damping reducers with increase in the frequency. Like these are the values which are measured on various cable length, and that's why the selection of cable, the damper, whether one has to, it has to be a frequency dependent damper or not, that those things also one can decide about that. Now, like we have seen about the dampers, that is 3 to 4% of the logarithmic decrement to be provided, that is the maximum value. But what has to be the limiting value of cable amplitude? That is, it has to be lower than 1 time the diameter of the cable. That will be ideal, but if it is not possible, at least it has to be less than like 2 times the cable diameter. That is from the comfort criteria. So we have to see two things. One is with respect to the structural characteristics, and another is with respect to the, you can say, the comfort criteria. So some of the key points, just to summarize, like cables with more than 80 meter, they are susceptible to vibration, whether like in extra dose bridge or cable stayed bridge, like you need to look into that. And surface modification that helps to address the concerns related to this rain wind induced vibration and vortex induced vibration. And you can decide about the type of damper to be provided, depending on that scruton number estimation, and additional damping of 3 to 4% that may be required for vibration control, because the cables are having inherently very low damping value, and it has to be decided based on scruton number. And internal elastomeric damper to be used for cables with length less than 150 meter, and internal, you can say, hydraulic damper for cables more than 150 meter. External dampers to be used for very long cables, and even like you are providing an internal damper, there can be a provision made for installation of external damper in case like some necessary comes in the future. Cross ties, they may be used as temporary measure or prior to installation of dampers. That actually helps to reduce the length of the cable and try to separate out the frequency if they are matching with that of the deck. But again, like there are certain inspection and maintenance issues also. So, but that is a cheap solution, I would say. Combination of surface modification, dampers, and cross ties that would be used for vibration controls. And I just discussed only few type of dampers, but I think this damper industry, there is a lot of research going on, and some new materials are coming, and also new type of dampers are also being developed. But one has to ensure the efficacy of such dampers prior to installing them in the bridges. And we can check the efficacy with the field measurements of that is the frequency measurement and damping of stay cables. And I just give a how like we can excite the cables so that like we can measure the damping and frequency. So this is a presentation for you to design the cables, stay cables in extra dose and cable stayed bridges. What are the type of vibration and how we can control the vibrations. Thank you very much.
Wow. My voice is audible?
Yes, sir.
Yes, yes.
Madam, excellent presentations. There are a few questions. I will tell Vikas to read those and then to please reply. Before that, I have one or two small things. that the life of structure is, say, over 100 years,
Yes.
whether it is a cable stay bridge or extra dose bridge. But then how to prevent the corrosion part, because these cables are all exposed with
Sir,
epoxy, whatever we put. Is
sir,
it
actually,
adequate, or we have to do proper regular maintenance of that?
no,
That is
no.
why.
See, corrosion protection mechanisms are there. I have already explained there are multiple layer of protection given for the strand and the cable. So I think, sir, more details are there in all these PTI guideline and our IRCSP 36, FIP 89, etc. Because this one is I have dedicated it.
That means after this, there is no
There is already that there are provisions. The corrosion protection is also now provided for the cable, so that they don't get corroded.
that means it's life, no corrosion till its final life. You mean it
Means
will
like
withstand 100 years. This corrosion prevention, whatever mechanism we are doing, can it last for 100 years?
No, sir. I think Dr. Lakshmi Madam has disconnected.
Okay.
Maybe internet issues, some internet issues.
So let's wait, because see, there are a few more questions.
Yeah, sir. There are few questions in the.
Just try to connect with her.
Yes, sir. Yes, sir. I'm calling her.
sir, actually there was some internet issue.
I know there was some problem. Good that you are still there. Then just I will ask only you spoke galloping, vortex, drag. Just being a layman, just repeat about this once again.
Sir, galloping basically it is a divergent oscillation, and it can be checked like our DCL by D alpha plus CD, if that can be checked using the Den-Hertog criteria. Actually, it is because of the negative aerodynamic damping, the oscillations are increasing very rapidly. So we don't want any divergent oscillation to happen on any of these structural components. Either it is flutter or galloping, we don't want that to happen. So that's why we want to prevent it from happening. So we need to take all necessary precautions for that.
Right. Then my final question is that construction and maintenance challenges in the particular, because it's such a sensitive element of the structure. I mean, just one or two lines on that. The construction and maintenance challenges in such type of bridges.
So these are, sir, the construction, there are many construction challenges during the long span.
Because now recently the Bihar 3 bridges just suddenly collapsed. In the short interval. So that is so we have to take suitable measures in planning, design, construction, because see, any bridge now, long span bridges, whether it's extra dose bridge or staying under bridge, we need extra precaution in the construction.
So, sir, actually, ma'am has again disconnected.
Now, Vikas, just madam will reply the questions. Please read those questions.
Yes, sir, ma'am has disconnected. We will wait for joining.
Okay, we'll wait. Huh? We'll wait.
Hello.
Tell the listeners to wait.
Yes, sir. Actually, there is an internet problem with madam. So she said that the
Just telephone her. If not possible, then we'll conclude.
yeah, yes, sir. Yes, sir.
Just try
Possible नहीं है
once.
उनके लिए. Yes, sir. Join करना
Just
possible नहीं है.
so then see. I mean, let's conclude.
Yes,
Thanks
sir.
to the audience who have spent the time to listen this. Now our next webinar will be on 25th of July. Again, same time, 5 p.m. on different topic. So please do then, get benefit of that. Right? Okay. Thank you, everybody, all the participants. So thank you.